What was it that made that example particularly simple, apart from the fact that I did it for you? What made it easy? The old machine.
Straight line depreciation.
So that made it easy, but also what else did? Yeah, so we had the convenient feature that the old machine had 5 years left and the new machine had a 5-year life. And the obvious question next is, well, what happens if they were different? How would we deal with that? Because they'll be doing different things. So let's look next at that situation. So this is comparing mutually exclusive projects with different lives. So let's look at a simple example as usual. We're going to do a comparison of two machines, A and B. And they perform exactly the same function in the sense that they have the same production each year. And we're going to therefore focus on the costs, and in particular we're going to look at the real costs. So we're going to make sure we compare across years in an appropriate way by working at real terms. If we were using nominal, they would have different purchasing power and wouldn't be comparable. So we're going to work with real costs. Now, A costs 20 to buy, and it lasts for 2 years. At date 1, so at the end of the first year, there are some maintenance costs, and we anticipate they're going to be 6. At date 2, we're going to have some more maintenance costs that have accumulated through the year, and they're going to be 4. If we calculate the present value of that at 10%, we get 28.76. B is a machine that lasts for 1 year. It costs 10. During the first year, it has maintenance costs that accumulate to 5 at the end. If we discount those, we get 14.55. So can we argue that B is a cheaper machine because it has lower costs? 14.55 versus 28.76. No, because clearly different lives, so somehow we've got to adjust for that. What's an obvious way of doing that here? How can you make B comparable to A? So at date 1, exactly, we can buy another B. So we've got a sequence of 2 Bs, and that's going to give us 2 years. So let's look at what we get if we have the sequence of Bs for 2 years. So at date 0, we buy the first B. That gives us 10 as a cost. At date 1, what happens with the first B? Well, we've got 5 for the old one, and then we buy a new one for 10, so we've got 15, and then we have 5 at date 2 for the maintenance cost. You do the present value calculation, you get 27.76. So the costs are lower than for A, so which should we use? B. So B is the preferred one here. Now, that works out fine in this example, but where would it be a problem to do this?
You have 3 years and 2 years.
If you have 3 years and 2 years, you'd have to go out 6. If you had 8 years and 9 years, what would you have to go out to? 72, and so on. So the problem is, if you've got different numbers, you're going to have to go a long way, and that takes a lot of time. So what we would do instead is another method. What we want to try and find out is what's the average, in some appropriate sense, cost for the machine A and machine B. Now, if we just took the costs and divided by the number of years, what would we be ignoring? Time value of money. So what we want to do is to find a constant amount each year, which is effectively taking account of the time value of money. We have a constant amount each year. What do we call that? Annuity. So instead of dividing by the number of years, what do you think we divide by? The annuity factor. Okay, so what we're going to do is to find an equivalent annuity and the way that we're going to do that is to use our formula. We know that the present value of an annuity is the annuity payment, and then we're going to multiply it by an annuity factor for X years at R%. What we're trying to find here is the equivalent annuity, in other words, the annuity payment. That's going to be the present value of the annuity divided by the annuity factor for X years at R%. Let's do that first for machine A. What we've got is that the equivalent annual cost for A is going to be what? Which one do we take? We're going to take the total cost. We want to take the total present value of the cost. So for A, we're going to take 28.76. We're going to divide it by an annuity factor for how many years? 2, because that's the life of A. And we're going to use our 10% discount rate. If we work out what the 2-year annuity factor is, it's 1.736. So we divide 28.76 by that, and that gives us 16.57. The equivalent annual cost of B is going to be our 14.55, which is the total, and then we divide by an annuity factor, this time for how much? 1 year, yep, at 10%. If we work out what we've got 14.55 divided by 0.909. If you work it out, it's 16.005. So if we think about what's going on in terms of our timeline, A costs 26.4, so the total present value of 28.76. If we pay the same amount at the end of each year, it's 16.57, 16.57. That's the equivalent annual cost. That gives 28.76 as well. So this is the cost per year, the 16.57. If we look for B, B has 10.5. And we know that's present value of 14.55. And then the equivalent annual cost of B is 16.005. That also has PV of 14.55. So what we're doing is finding the constant amount which gives us the same total present value. Clearly B is better because its costs per year is lower. So we're going to choose. Any questions on any of that? Would this be a good method to use for personal computers? What have we assumed here about machine B in the second year? It's exactly the same a year later, but if it was a PC, what would we know a year from now? It would be much better. So what we are implicitly assuming in this calculation so far is zero technological progress. If we have some technological progress, then we need to take account of that. Final thing to stress, as I mentioned at the beginning, work in real terms for these kinds of problems. Otherwise, you're not comparing like with like. Yes?
So if it was in the nominal term and we had specified it, we would have provided it by the inflation.
Yes, if it was given, the information was given to you in nominal terms, switch it into real terms, and then work with that. So the way you do that is what we saw last time. You divide the cash flows at date t by 1 plus the inflation rate to the power 2. And to get the real discount rate, you take 1 plus the nominal and divide by 1 plus the inflation and subtract 1. Other questions?